So one of the last things that we mentioned last session was quite an important concept. It's a way that it's one of the ways that we measure the effectiveness of our model. And when we say effectiveness in this context, we're looking at a predictive model. So that's your supervised learning, where we're using one or more predictor variables. Those would be our x's to derive our output value, our yi's. And I'm referring to the mean squared error. I can't get this to zoom in for whatever reason. Don't ask me why. And okay, here we go. Mean squared error is this formula. I think it's probably a good idea to actually type it out. So we're in my Word file right now. I'll just give it the heading, mean squared error, and we're abbreviating it to MSE. And when do we calculate the mean squared error? What are the different inputs that it takes? Well, it needs the number of observables. It needs the number of data subjects. So we'll say let n be the number of data subjects, i.e. observables. Let yi be the, we'll just call it the output variable. There's a better word, but it escapes me. The output variable. So think of, in the examples that we've been discussing in the book, think of wage as well as sales volumes in the marketing example, where it was a company advertising using 3 different media types, TV, radio, and I guess online advertising. So let yi be the output variable of each observable I. So I is going to run from 1 to n. And f hat is the, what's the model, isn't it? F hat is the model, and we're going to take f hat of xi. F hat of xi is the estimate for each observable I. Now, we need a measure. We need would like to quantify the discrepancy between actual and expected. Actual is the, well, self-explanatory, isn't it? The actual output. So for the time being, we're working on the training data, but then in practice, you would want to take observables that haven't actually been used in the training. We might do some of this today, perhaps in Excel, or even in our studio, but probably it's best to start from Excel. Now, the formula is, you're going to take the difference between each actual quantity and expected quantity. So it's this difference. Now, for the simple reason that sometimes your yi is above your f hat of xi, and sometimes it's the other way around. You don't want some of the differences to be negative and others positive, because those might zeroize each other. You might get a an MSE which is incredibly close to zero in this way, only to find out that the errors might be significant, but they happen to be in both directions, so they would simply zeroize each other. So to avoid any of that, you could use the absolute value. If anyone's thinking of the absolute value, that would be a valid way of doing it. However, for reasons that we're not going to go into today, it is customary to eliminate any potential zeroization of discrepancies between your actual and your expected by squaring these differences. So for each observable I, we shall have this quantity. So that's the squared error, but we would like to calculate the mean squared error. So we're going to take the summation. We're going to take the summation. We're going to sum over all these square error terms for each observable and divide by the number of observables. This is our formula. We can compare it to what we have in the book. I've used exactly the same notation, and hopefully we're saying exactly the same thing over here. Now, my idea for this session is that we would do two things. First of all, I'd like us to go to this diagram where we sort of have a demonstration of mean squared error in practice. We haven't been given the data points, but very quickly, each point over here, that's your raw data. And we have so many of these. So we have from when X is 0 to 100, maybe we have 50 data points over here. Looks about right, maybe less than that. The black is the actual relationship, the actual. Now this is something you usually wouldn't know in practice, but it's the actual relationship between X and Y. Now, if you're asking, why doesn't each data point lie on the black curve? Well, that's because of the error term, correct? So taking a step back and thinking of the entire empirical process. What we mean by empirical is what you observe in reality. Think of in a laboratory, think of sending out surveys, think of just your own historical experience at school, when crossing the road, when traveling. So you have your empirical data, and we would like to create a relationship between Y and X. And we codify that relationship using the following formula. Y, that's your output variable. So for each observable, this is a, we could, if you like, we could write it as a, we could just remind each other of the equivalence. Let's see. So we'll use that arrow. And if you find this helpful, Y is made up of these entries. That's your Y. And X, probably easiest to just copy this, isn't it? X is made up of these entries. Now do remember another thing is that in the case of the X's, not the Y's, but in the case of the X's, each entry over here is in fact made up of P entries. So strictly speaking, this is a matrix. we could use the bold font to emphasize this. And then you have an error term. You have an error term. We're using epsilon. Epsilon. Again, it's probably easy to just copy and paste, isn't it? And epsilon. And what do we know about epsilon? Well, epsilon captures the error within the model. Now, why are there errors? Well, random noise creeps in for the simple fact that, or at least one of the major reasons is that there'd usually be more than, you're only taking a specific number of predictor variables. So think of wage. Think of an individual's annual salary. We can quite easily, within, I would say, a few minutes, if we had to pool our thoughts, we would very easily come up with a list of 100 different relevant variables that we would expect should have some impact on an individual's salary. You can even think of the different stages in one's life: childhood, primary school, secondary, which course one follows if they choose to further their education at university or at polytechnic or similar. Our model, you don't want to take, you don't want it to have more variables than necessary. So as long as your model is operating within an acceptable margin of error, then if you think of the price that you pay to collect that data, there comes a point where you have enough input variables to sufficiently describe and forecast the output that you're interested in for 90% of situations, like 90% of individuals. So the epsilon is the error term, and it needs to have a mean of 0. And we'll try doing this in Excel. Epsilon represents the error term and should have a mean of 0. So think of it at this point as contributing. There's a certain randomness. Epsilon provides the randomness. Do you see how hardly any of these data points are perfectly on the black curve? Well, the black curve is this part of the relationship between y and x. F hat, well, that depends on the model. And in fact, we've taken 3 models, right, over here. We've taken the gold model, or the orange model, the blue, and the green. It's these 3 curves. And we're trying to find the curve that captures the relationship between x and y. X may be made up of multiple components. In this case, we seem to have a simple single variable as our input, and this will always be the case. In fact, the output is a single variable. So let's just look at it in Word again, especially for those of you just joining. We intend to focus our attention on the calculation of the mean squared error. Mean squared error comes after you have designed your model, and it attempts to quantify the model's effectiveness at predicting the variable of interest. The variable of interest is y, and it is a function of this x. That x for each observation might be a single characteristic. So think of years of education, or you could have multiple characteristics, multiple aspects. Let's have a look at this in Excel. And okay, if I type, that should come up. And we have a question in the chat that's asking, would you usually benchmark your model? In fact, if I paste it, we can probably better follow. I don't necessarily have an answer to this, but we have one question that's asking, am I correct that you usually benchmark your model? Am I correct that you usually benchmark your model versus another and compare the mean squared error of both and see which one is best? Well, exactly right. If you only have one model, then you're really working, there isn't much to compare against. And in class, when we say benchmark, that's what we mean when I say compare. Yes, in fact, what is the book doing? The book is looking at 3 models, and it's calculating mean squared error twice for each model. And why twice? It's doing it once for the training data. So we have the training mean squared error, that's the gray curve. And we also have the test mean squared error. Now you would normally want to use the test mean squared error. What do we mean by test? We mean using data that hasn't been incorporated in the model, that the fitting of the orange curve or the green or the blue has not considered this data. Right. So I know I keep on switching back and forth. In fact, why don't we come up with a cubic relationship? Let's play God, just like the authors are doing. And let's just come up with a cubic relationship. And I might use Desmos for this. So I'll just ask you all to wait for me to open. Yes, please.
Can you re-explain the difference between training and test, please?
Yeah, definitely. So the idea is this. Let's go back to Excel. Let's say that you have a data set, and it has 10,000 variables. It has 10,000 variables, and so this would be the observation from 1 to 10,000. And then we will have characteristics. So why don't we stick to the wage data? So years of education years, employment years, maybe male, female, how many languages one speaks, perhaps. I'm just inventing over here. Ultimately, in this specific model, we're interested in predicting the wage, maybe even predicting the wage of an employee that's never existed, maybe an employee that's done 10 years in education, 15 years in employment, is a male, speaks 20 languages. You get the point. Now, the test data, so we have training data and test data. Training data, well, it's as the name suggests. It is what the model is going to look at. So the model, it's the raw data. You've sent out a survey. It's been filled by 10,000 different individuals. And you're going to keep that data in when it comes to training the model. You're training the model. The model is looking for patterns. The model is looking for a formula, for a relationship between these input variables and this output variable. So that's your training data. Now, what is test data? Well, test data is any data that follows the same structure. So maybe the 10,010th first observation, but hasn't been used to train the model. And these observations, so we could call these training. These are tests. It is a lot better. It is a lot better to use test data when calculating your mean squared error, for the simple reason that your model is already prejudiced in favor of the training data. Your model was built on the assumption that this data is true, that this data offers insights into a more fundamental relationship between wage and these variables. So data is data, but there is training data, and that's the data that we choose to train the model with, and there is test data. So I'll take just one more example, because I do appreciate this is not necessarily an easy distinction, especially for those of us who are relatively new to this line of inquiry. Let's take an insurance company. It has 20 years of data. For instance, we're interested in the number of claims, and I've used this example before, the number of claims each year, the annual number of claims. And we choose to use the full extent of that data. And we have a model, and that model is now making predictions. That model is telling me that next year, if I sell so many policies in so many countries in a certain ratio, 10% Germany, 20% Spain, then I should expect, now this is the model, I should expect that next year, given the features of the company's business plan, it's planning on selling so many policies in so many countries along a certain split, 10% in this country, 20% in the other. Once next year passes by, we can now look at the end of next year, we can then look at how many claims were in fact reported to the insurance company, and we can perform actual versus expected. So I don't know if that helps, or you need a follow-up question.
Yes, it did. Thank you.
Okay, very good. So we're in Excel. We're in Excel, and I said that we should actually go into Desmos first, and I'll just show you what I have in mind. I'd like to create a curve similar to the books. The book is playing God, and the book is saying that between y and x, ignoring random noise, ignoring epsilon for the time being, that we have this relationship. I don't think it should be too difficult, right, to create something similar to this in Desmos. Well, first of all, they're taking from 0 to 100 and from around 0 to 12. So we're going to work in this region. And then they have a curve that passes. There's definitely an easy way of doing it, but I think I'm just going to brute force it. See? Now, what do I need? I need it to open up like this. Why did I take a factorized? You wouldn't want to do it like this, would you? We've made life very difficult for ourselves. I think a more natural way of doing it is just writing it in canonical form. Let's do it like this. And see, we have like this. So, yeah, I just want to stretch it out, right? So if I want to stretch it out, maybe the approach I took earlier wasn't entirely without merit. No. Yeah, this is easier. This is easier. There's a bit of backtracking, but hopefully this allows everyone. I'm trying to save face over here, but it allows everyone to digest. Bit of a tongue twister over there. To digest what we're saying. So let's see. I want to stretch it out. So yeah, exactly. I could have probably placed this in a single, but yeah, it does need to be perfect, but definitely an easier way of doing it. I could have maybe taken 3 points. If you have 3 points, or maybe 4 points, that's enough to fit an exact cubic. So I'm going to abandon this and let's take x squared plus x cubed plus x squared plus x plus 1. And what I want is, I want to stretch it out. So if I want to stretch it out, maybe I should have taken, that's getting kind of stuck, aren't I, over here? If I want a cubic that does something like this, but over 100, surely all I need to do is take these sufficiently, because once we have this cubic, we can then use it in Excel, and we'll add some random noise, and we'll actually get the data points. And class, I keep on saying class, force of habit. Let's see. So I would like maybe fit a cubic polynomial to the following data. And is there a calculator that does this? Or maybe we'll just abandon, we'll just abandon the idea of a cubic. And maybe we should have started with something simpler. So for instance, if I wanted to pass like this, maybe we're getting somewhere now. And okay, yeah, okay, very good. So I think it's not cubic. I realize that, but at least it now has the the kind of the breadth that we're after, given that it's from 0 to 100. Yeah, let's maybe do 100 minus x just to get it. Okay, yep, very good. And now we just want to, yeah, excellent, excellent. Now we just need to scale it down. Oh yeah, very good, very good. And we said we'll only take, okay, very good, very good. So hopefully it has some of the features that this back curve has. Now, probably should quit while I'm ahead, but if I do 100 minus x, yeah, that's actually pretty good, isn't it? By pretty good, I mean, it looks like what the book has. Does it need to be like the books? No, not at all. I agree, but it's a bit of fun as well. So we have a minimum and a maximum. And hey, it took some time, but we kind of got there, right? What if I scale like this, or I scale like this? Okay, so this is going to be our function, and I will paste this into Excel. Paste this into Excel. We're going to type it. We're going to type it out. And let's take 100 variables. So from 1 to 100, from 1 to 100, and the formula is, let's enlarge. The formula is, I could use reciprocal maybe, but 1 over 20,000 times this. We could square. So I prefer using brackets wherever I can, just to avoid any potential ambiguity. 100 minus, well, that's wrong. 100 minus that plus 5. Okay. So this is without the error term. This is without the error term. So this is x. This is f of x. Let's have a look if this resembles what we have in Desmos. And it does, right? So that seems fine. Could place a chart if you like, but we don't really need that for the time being. And I would like to include an error term. Assuming I'm still sharing Excel, I would like to include what we've been referring to as an error term. Okay, so how are we going to get this error term? We're going to use something called normal distribution. Now, I don't really have that much experience using it in Excel, believe it or not. But if I say norm distribution returns the normal, so that's not what I want. And I think this is what I want, returns the inverse of the normal cumulative distribution for the specified mean and standard deviation. So what I think I need to do is, I need to give it a probability. I'll just give it a random probability from 0 to 1. Now, how does one do that? Yeah, like this. I'm going to specify the mean. We said mean 0 of the error term. And now standard deviation, I'll take a standard deviation of 0.25. I may choose to change it. Now, strictly speaking, you should never hard code anything. So the 0 and the 0.25 should really be over here. And I'll call it error mean, standard deviation mean. Definitely better ways of labeling these things, but we'll just stick to what I've typed over here. We'll say 0, we'll say 0.25. By the way, I don't know if you've ever seen this, but you can actually, it's the different font. In a second. I want Calibri Light and 12. It's the difference in font between this. But if I specifically said Calibri Light, I don't like it when I have different fonts in my workbook. Do you know that you can give cells names in Excel? It's actually very similar to what we're going to do in R. And the way you do it is this. You just select the cell and do Alt, M for formulas, M for define name, and D for define name. So error mean, I'm going to do the same thing, Alt, M, M, D, standard deviation mean. And now I can tell Excel, error mean, see it? It's saved in Excel and it's selected B1. And I can write standard deviation mean. So this is the error term. This is the error term. Let's have a look. Let's have a look just at the error term. Just at the error term. Remember, the error term is present in all models for the simple fact that a model is a simplification of reality. And by simplification, I mean it's not allowing for all the variables that influence an output. I mean, think of a coin toss. Strictly speaking, if we turn to classical physics, if you know all the variables, the weight of the coin, the exact density distribution of the metal, the humidity, other environmental factors, the angle, how high it is from the tabletop that it's eventually going to land on. Strictly speaking, that's not a random event, is it? There comes a point where, at least theoretically, we could, to a good degree of accuracy, and the thing about a coin is it's heads or tails. So if the accuracy is slightly off, you might get a significantly different result, right? I mean, think of if you're betting all your net worth on a coin toss. So all of a sudden that coin toss is, I don't know, you're betting the family house. That coin toss is now you win $500,000 or you lose $500,000. Getting it wrong means not getting it wrong. The $500,000 was actually 400K, but the $500,000 is now negative $500,000. But strictly speaking, if you knew all the variables, then you've removed the element of randomness, haven't you? So this is what we mean by this error term. The error term is an element of humility. The model is recognizing that, I wouldn't go so far as say by definition, but practically by definition, it is limited. It's not presenting itself as picking up all the patterns and relationships in reality. Now let's look at this error term. Let's just plot it like we did with the...
Sir,
Yes, please do tell me.
where did you get the 0.25?
I just invented something.
All right, and
Just think of it. Just think of it. Let me, you know what? That's a really, really good question, and I'm going to answer it. And I know you have a follow-up question, so just bear with me for a second. Let me show it to you this way. And I'm going to give you a very good idea of how those two values that I picked totally arbitrarily, how they're going to impact the contribution from the error term. So what do I need to do? I need to write insert, recommended chart, and OK, but I'm going to cut it. I'm going to go all the way to the top, and I've placed it over here. And I think it's F9 each time I'm generating these error terms. So what do we notice, class? We notice that the x-axis, so y equals 0, we shouldn't call it y, should we? We should just call it epsilon. That epsilon is the vertical axis, is basically the line of symmetry. You have as many points above the horizontal as you have below, roughly speaking. And we have this, can I say it fans out? I think I can, right? Most of them are between 0.2 and a negative 0.2. And then you have what, in this context, would be considered outliers. This is an outlier, and this is an outlier. Now let's see, what difference does the 0.25 make? Well, I think to see that difference, we better format the axis. Why am I doing this? It's so that it doesn't move each time. So let's do it like this. This is going to increase the variability. So from 0.25, I took 1. The variability has increased. The variability has increased further. And of course, the opposite direction applies as well. Now, to the naked eye, they are all on the x-axis. It is to 2 decimal places at any rate, it is a 0 error term. You want, this is intuitively, it must be the case, you want to reduce the magnitude. Maybe I shouldn't use magnitude, it's not a vector, but you want to reduce the minimum and the maximum of the error term. Yes, you had a follow-up question. What was it? Unless I've answered it.
I think you answered it.
Now the mean would translate everything up or down. If the mean is 2, now everything is going to be roughly orbiting. I prefer a different word. Why am I using orbiting? Is going to be roughly to the left and to the right, above or below is what we should be saying, an epsilon value of 2. But epsilon, we want epsilon to have a random, we want epsilon to have a mean of 0. So there we go. All good?
Yes, what I can't get is why you have a different value of error term for each x value.
I agree. So although if they had the same, when I add this to this, if these were all negative 0.29,
They
it would
wouldn't
just,
cancel.
I was going to say, it would just shift this curve down by 0.29. Nicole, the idea is that, and this is a concept that you probably haven't encountered before, the error term is what we call a random variable. I don't agree with the chat. The chat is saying, let me get that again. Isn't the idea to cancel? I wouldn't say that the idea is to cancel, unless you mean kind of like they're balancing each other out. And yes, so maybe I do agree actually with that comment. And in fact, you're saying that's what you had in mind as well. So I just didn't understand you. Okay, so now we're in a position. Now we're in a position to create this. And this is reality. We're playing God. We're playing God, with the exception of epsilon. But even as God, even as an omnipotent creature, we could say we know F, and we know for a fact that only allowing for these predictor variables means a mean of 0 and a standard deviation of 0.25. So let's paste it downwards. And what I'll probably do is I'll now copy and I'll paste numerically. Otherwise, Excel will keep on randomizing each time I perform a calculation. In fact, it's already randomized. As soon as I paste it, it's already randomized once. Okay. Now we can plot. Now we can plot. And here we go. Unless we take a larger error term, let's take 0. Whatever, 0.75. Yeah, very good. Very good. We do okay. We do this. We do this. And we do this. So this is our data. This is now our data. What data is it exactly? Well, it works on, it's based on two terms. It's based on f of x. That's as much as we know using one or more input variables. You could think of it as one input variable over here. 0, 20, 40, 60, 80, 100, 120 if necessary. And our output. The epsilon captures the limitation of the model, the limitation that arises from not allowing for every potential predictor variable, every potential attribute that has an influence on the variable, on the output. Right. Now, so that is our raw data. That is our raw data. Now we want to fit a model. We want to fit a model. But remember, we don't know, when it comes to fitting the model, we don't actually know this relationship. You need to think of this process in exactly the reverse. You will collect this data. You will send questionnaires out. And let's say that, for example, the horizontal is age. And you ask individuals, you ask 20-year-olds, you ask individuals in their 40s and their 50s. Let's see, what's something that might make sense? Hours of sleep? Not really, right? But think of something that's going to peak. For example, number of hours a week watching a specific program. And it seems extremely popular with the 60-year-olds and the 70-year-olds. Now, we want a relationship. We want to create a model. And we have three models over here. We have a linear model. We have the green model, which maybe is the most fitted. And then we have something smoother in the blue model. Okay, now let me have a think about it. Best thing is to go into our studio and try and get this data, although I'm not entirely sure how I would do that. There is a way that you can read an Excel file. So if I open a new Excel file and I paste this data, and let's just give it a name. Let's just call it raw data. Perhaps observation as well. I'm not promising you this is going to work, and I'll be quite disappointed if it doesn't, although to be honest, I'm not expecting it to work, because I just have very limited experience transferring data from Excel to our studio. But let's go into our studio, which I'm hoping is already open. And I'll actually share the book for the time being. And let me see if I get this to work. I need to save the Excel file. Save as. Go into downloads. Just call it raw data. And there's a package called, so I need to library. No, not open SSL. Let's see if I find it over here. XLS, XLSX. Uh-oh. No package. Interesting. Give me a second, please. Actually, we can, you can see what I'm doing. I'm just going to go into the browser and search this. So what are we going to search? To my knowledge.
I think it's read Excel.
Is there a package called read Excel? Let's check. Install XLSX. Why is nothing coming up? So read Excel. Very good. Fingers crossed. So we're installing it. I definitely had one recent. I was using it with open. Let's load it. Library. Read Excel. Let's have a look at the commands. import Excel files into R, supports XLS and Excel SX. But what are the functions? What are the functions? So let's have a look. But do I need the tidyverse? Let's have a look. So what we need to do is we need to do read Excel. Read Excel. Why is there an underscore example? So read X. Get path. Let me just check with the one I'm familiar with, which is, to my knowledge, open Excel. Yeah. Let's have a look. Read. So why don't I have this package? Why didn't it come up when I searched? Let me just try again. So you go in packages, you go on install, and if I type open, okay, here we go. Install. Then we have, yeah, always do yes when it asks. Okay, I must have installed it somehow. It's not done yet. You'll know it's done once this red icon, I think that's stop, that's to manually terminate a script. Let's say, for example, you have a code and it enters an infinite loop. Then you would want to probably stop that, otherwise you're just going to remain with the compiler running for an infinite period of time.
Can I ask, are we meant to understand what's written in the console?
I'm not understanding it. No, I don't think so. It would be a plus, I would imagine, but you can probably live without any of this. All it's doing is it's installing a specific package. The reason why I'd like to install this package is it's the one that I have some familiarity with when in terms of just reading and writing Excel files. It's taking a lot longer than there might be conflicts. I may have installed packages recently and there may be conflicts between them. If that's the case, let's just give it a few more seconds or minutes. In the meantime, while it's doing this, let's go back to the raw data. So this is your actual data. So this is yi. This is yi. This is your actual data. And imagine that, let's go into Desmos. Imagine that your model is a linear one and creates, let's see. What if I say 1/20x plus 5 or plus 7. Let's say that this is our model. It's not necessarily doing a very good job. After all, the relationship appears to be cubic, and we're using a linear f hat. Yet we decide to use this blue as the model to predict the white. So let's go into Excel. And now we're going to have our f hat of xi. So what do I need to say? Well, we had a formula in Excel. I'm just going to type it, 1 on 20. Again, you really shouldn't have any hard-coded numbers. Plus 7. And this is what we end up with. This is our expected. This is our estimate. By the way, in the meantime, I'm looking at our studio. The package has been installed. But let's look at this. Let's look at this. So for every observation, and remember, this is our test data. This is our test data. For every observation, we have the actual output, the actual, what else could I call it? I'm going to stick to output, the actual yi, and our estimate. Now we can calculate the mean squared error. How? You calculate the square error by subtracting this from this and squaring. Mean squared error is we take the summation, and I'm going to hard code again, divided by 100. So for this specific model, the mean squared error is 5.14. Let's keep in mind what this is. What we're saying is that on average, if you had to take the summation is 513. But on average, if you had to spread it out evenly, uniformly over each observation, then there is a square error of 5.14 arising from each observation. And in fact, you can even just shade, and you should see the 5.14 over here. Oh, just an Excel tip, something I only discovered very recently. If you click it, it copies the number, which is sometimes very useful. So if I just go here and do Control V, it's that number that we had earlier. So this is the mean square error for this specific model. Now, this is what we had in the chat earlier. Is it too high? Is it too low? You can't really, in the context of a single model, there isn't really much that one can say. It really becomes useful when you have multiple models, and this is exactly what the book is doing. And looking at the red curve, which was used on not training data, test data, it's the same principle, it's just different data. From these three mean squared errors, on the basis of the mean squared error, this is the best model. Now, there might be other considerations that one would like to consider, but this is the best, this would be the best model with respect to the mean squared error. Now, in the meantime, we've actually got this to work. So if we load it, and why doesn't one? Never really figured out. Sometimes suggests and sometimes doesn't.
How did you know which graph gives the best interpretation?
Because you want to minimize the mean square error.
All right.
So
All right.
the orange model has a mean square error of 2.1. The blue is a lot less, and the green is somewhere in between. In fact, to a certain extent, it is what you would expect, because the green is overfitted. We have followed the data maybe too closely in certain regards. And the orange is doing a really bad job. The orange isn't even recognizing the non-linearity of this data.
Mm-hmm.
Okay, so we can, class, whenever you want to use a package, you could look for it over here, and you could just stick it. Okay, so now it's library, open XLS, that's running. Let's have a look, open. Now, what are the commands? The commands are, if I want to read Excel, yeah. So it is read XLSX. Now I need to give it the file name. So in inverted commas, I need to give it the file name. Now, if I place it, I'm working, if you go into files, there's a command called WD, to my knowledge. No, it's not WD. It's W something. It gives you the workspace, but it's not WS, is it? W. Okay, I'm just guessing now. But there's a way to get it's either the working directory, but WD didn't work, and it tells you exactly in which file. If I tell Excel this file without specifying the entire path, if I have saved an Excel file as raw data, if I just tell it raw data and it's saved in the folder that RStudio is kind of currently taking as a default, then it will look in that folder and it will see if it can find it. Don't ask me again. I'm not entirely sure. That's why we're doing these sessions after all. It doesn't mean we're going to answer all questions, but we will do our best. So instead, let me just give it the path. Give me a second, please. Oh, by the way, shortcut Windows button E opens your file explorer. Windows button E, you might want to try it if you're following from your computers or whatever. Give me a second, please. And what do I need to, what do I need to type? I think I need to type C this. Actually, it's the other way around. I think user Stewart, but without T. Don't ask me why. It is just my specific computer omits the T. Downloads. I'll be really surprised if this works. Raw data. Let's type it. Raw data dot XLSX. File does not exist. Great. Let me just double check. Downloads. Okay. Yes. Well, welcome to the joys of coding, where if you're off by one character, actually worse than that, it could be even just a case of uppercase versus lowercase, then it doesn't work. And code is a lot like that, right? It either works or it doesn't very often. So we actually have our raw data now. So now that this has worked, why don't I also include, I'm going to share the file that I'm using, which is this one over here. But I'm going to include our model's predictions. And we'll call this expected. expected data. I'll save it. Okay. Surprised it took so long to save it. We'll do it again. And fantastic. We now have these entries. In fact, we could save it as a data set. So we could call it, for example, empirical data, or just empirical. Meaning, whenever I call empirical now, so for example, I could do head empirical. We now have the first, however many, but by default, it's 6 rows. I could only look at 2 rows. You could do summary of the data. And this will apply your sort of your O-level statistics to it, to each column individually. So what is it telling us? But this is a bit meaningless, right? Because it's taken observation as sort of a field. I could have probably, in fact, I might do that right now. Apparently, we can delete this. We don't need it. We'll save. Notice I don't need to close the workbook. Beg your pardon. Okay, everything seems fine. We'll empirical like this and like this. So the summary function is extremely convenient to quickly get an idea of the shape of the data in each covariate. What do I mean by covariate? I simply mean field. We have the raw data field and the expected data field. Now, this isn't, the data isn't that interesting because there aren't the input. Yeah, so maybe I should have kept the input variables because those x's were variables, weren't they? I just so happened to take from 1 to 100. Never mind. Let's stick to this now. And we would like to calculate the mean squared error. So let's tidy it up a little bit. Actually, I'm going to do it all over again. Hopefully you find some. If you want to clear the console, it's Control L, and then you delete if you have anything typed. If you have anything typed, that needs to be deleted. But then Control L clears any residual artifacts from running functions or running the script. So what would you do? So you turn on, you'd load R, you start with library, and it was open XLSX. Okay, this means I now have access to all the functionality and any data sets. I wouldn't imagine that this package contains data. It's not really what it's designed for. Now we're going to create the dataset empirical questions.
So you're still sharing Excel.
I do beg your pardon. Yeah, always let me know. Empirical, and we're going to write read dot, and I press tab, and it already presents the parentheses. And what do I type? Well, in my case, I type, I'm working in my C drive. It is not this slash, it's that slash. It's a bit annoying. Users, in my case, Stuart, but my laptop seems to omit the very last character, my name, for whatever reason. I saved it in the downloads file. And I named it raw data.xls. It probably wouldn't work without that extension. There we go. You're seeing it saved over here. There's a nice summary, and it's telling you what it is. It is data. It is not a function. Neither is it a vector. It is data. It is data. In fact, you could ask R to tell you what kind of data it is. Is it a matrix? The command is class, and it tells me it is a data frame. If it was a matrix, it would have told me it's a matrix. You get the idea. Okay, now let's look at just a few rows of data. Head empirical. There we go. Just gives you an idea. First, not that the first 6 entries are necessarily representative, but it gives you an idea. Let's put it that way. If you want a really good idea, the best one is str. Str empirical, and it's kind of row by row. Each row is a column in what we had earlier. There's the raw data field. That's numerical, gives you the first entries. Expected data, that's also the first few entries. Now, how do we calculate the mean squared error? I'm not entirely sure how. I could create a new vector. And why don't we call it empirical raw data. Notice that now that's been stored under a vector, just values. And we'll call f of x. By the way, best practice, there should be a space over there. Sometimes you'd have a negative, and then it would be like 2 dashes. That's one reason why you should keep a space at all times. And this is empirical expected data. Now that hasn't worked. Okay, because probably doesn't want me. So I'll do, let's call it expected and actual. And I want to remove y. I'm not entirely sure how though. Anyway, we'll just have to keep it over there for the time being, unless we just maybe do null. Okay, it's still there, but it doesn't contain anything. Now, how do you calculate the mean squared error? You want to create a new vector of values. I'm referring to these values over here. The 8.85, the 7.50, the 11.05, etc., etc. And I think it's the great thing about R. It's an extreme natural way of doing this. You just do expected minus actual. Let's see if it works. I'd actually be surprised if it doesn't. It's one of those cases where I'm pretty convinced this should work. And it's worked. Do you recognize these? Interesting. 22.789. Didn't we have 8.85? They don't seem to line up for some reason. So I've done expected minus actual. So the 4 minus the 8. And why is it 22? So actually something seems to have gone wrong over here. Although I'm not entirely sure. What if I did expected minus expected? Surely we get zeros now. So that seems fine. That seems fine. And yet when I do this, we get 22.785. We'll get to the bottom of it. Not entirely sure what's wrong over there. If you think you've spotted why we're not getting the numbers I was expecting, do let me know, please. Now let's create the mean squared error. And you know what? Let me first just do it as a calculation. And I think we'll take this opportunity to show how to define functions in RStudio. Yes, what do you think?
I was going to ask what's the purpose of empirical?
That's our data set, isn't it? The empirical is just the name I've given to my data. This is what we have. This is what we had in Excel. We have the raw data, which was that cubic curve, and we have the expected data, which is based on the linear curve. Do you agree till there?
Yes, yes.
It's just what we have in Excel. It's just what we have in Excel. It is these two columns, the actual and the expected.
Mm-hmm.
We've placed it in R now. If we want to manipulate the data using R, the very first thing is that you need to load the data into R. And that's over here. By the way, there's this really convenient thing. I think if you double click, it actually shows it to you. You can actually look at it kind of like an Excel format this way. It opens a new tab. All I've done is I've just
Yes, yes.
all I've done is I've just clicked empirical. Does that answer your question?
Yes, yes, thank you.
Okay, very good, very good. Although I'm still slightly concerned with this 22.785. Anyway, now how do you calculate the mean squared error? Well, now I just need to sum each value in this vector. So I do sum of SE, which is that number, and I need to divide by 1,000, and I'll show by 100. I'll show how to avoid this hard coding, which is 86.23, which is a bit disappointing, isn't it? Because we needed to match this 5.14. So that would mean that something has gone wrong. I'm not entirely sure what has gone wrong. I've done the empirical raw data minus the empirical expected data. Let's look at a single value. Let's do EXP, which is just the expected data. And you could say 1. That means the first entry. And then we do minus actual, the first entry. And then we square. And that is 22.78. So why didn't we match? Did I paste the wrong thing into Excel earlier? I pasted this. And yeah, I pasted the square error. So sorry about that. This is what I was meant to have in the second column. Let's save it. Let's run it again. Okay. Now, yes, because I need to define again the XP. I deleted those lines of code. Empirical raw data, ACT, just for actual, empirical expected data. Let's run both of them, EXP and ACT, just for expected and actual. Remember, actual is expected is what the model is telling us. The model is telling us you should expect this output. You should expect these outputs. The actual is, well, the actual outputs. And there will always be, you would expect some discrepancy. The model will not get things correct, although there are gradations when it comes to the incorrectness of your model's prediction. So how incorrect was it? If it's close enough, depending on, and of course that's highly subjective and usually a function of the context, then the model is fine. Okay, so let's calculate the mean squared error. And the mean squared error is the sum of the vector exp minus act squared divided by 1,000 and divided by 100, right? It's 100. It's 100 data points, and that's 5.13. So hopefully, having first done it in Excel and now in R, we are perhaps in a better position to follow what's going on here. Now, how could I avoid hard coding the 100? I could say the length, and length means the number of entries. The length of, for example, the exp vector. That's just going to be 100. This is going to be 100. But of course, if I change it, if maybe next time around I have 1,000 data points, I don't need to change the code. It would still give me the correct mean squared error of 5.13. So that's one way of doing it. That's one way of doing it. I can also show you. Can I take empirical version 2 and do a C-bind? Not entirely sure this works. The original empirical with the squared error term, which is this. I'd actually be surprised if it works. But it has. It has, in fact, given me what I was after. So I've now sort of created a new data set. It has the same 2 columns, the same 2 fields as the first data set, but it's now included a second data set. And that's where it's calculating the square error for each observation. Okay. You could also ask, what was the worst square error? You could do max. Take this vector. This vector contains, maybe I should just show you the vector. See? It's all these, although why don't we round and do 2 decimal? So these are your square errors. These are your square errors. The actual output minus the predicted output, all squared. The square error, probably the previous page. The square error must be calculated for each observation I. For each observation I. How is it calculated? You know exactly how it's calculated. Okay, very good. Yes, I'm seeing the chats. Thank you for messaging. And if I want to see the worst square error, it's just the maximum of this. So the worst square error is 46.1. Now, there's probably an easy way of actually finding which row it is, but I'm just eyeballing it. And it's this one. It's this one. It's to be expected, right? That's where our model, in many ways, is at its worst. That's where our model is at its worst. Not only are you taking this difference, you're squaring that difference. So it's increasing quadratically. And just repeat it a second time. This is the error. This is the error between the prediction and the actual. And then not only that, but you square it, which is of course going to magnify that error quite a bit. Okay. Now, was there a better way of doing all this? Well, let's think a little bit about it. I'm going to do Control L. That's removed everything in the console. I'm going to clear the entire environment, which means now if I ask it what is MSE, it's going to tell me there's an error because MSE is no longer stored anywhere. I'll delete everything. And we're back to our empirical data. Say head empirical, just to get an idea of what we have. Or I think probably we could argue STR does give you perhaps more insight. Well, not really, actually. It gives you a lot of the same. Probably summary gives you the most insight. So STR of empirical, these two fields, there are 100 observations. Each observation has two variables, and we have our raw data and our expected data. What we're leaving out from this data set is the actual input variables. We don't really, well, we did take from 1 to 100. I guess those are our input variables, but we don't need them to calculate the mean squared error. The mean squared error needs the number of observations, the actual output, and the predicted output. Predicted output, what is doing the predicting? Our model. And I just like to remind you, we took this model. It had to be linear. What do I mean by had to be linear? I wanted a linear model, but the 1 on 20 and the 7 have been chosen entirely at random. What I could say at this point is, what if I do lm? What does the lm function do? It's something I haven't mentioned yet. You can ask R what lm does by doing question mark lm. And lm is actually fitting a linear model. So I could, instead of taking this relationship in Desmos, I could have asked R for a similar, so to speak, relationship. lm. But we need the inputs, don't we? We need the inputs. So it's actually quite a bad idea to exclude them earlier. So let's call them our xi's from 1 to 100. I'm going to paste numerically just in case. It's probably unnecessary. I'm saving. Now we have this. So our observations happen to be, just think of it as, we asked only one person, age 1 year old, how many hours they watch, how many hours a week do they watch for a certain program. Then we asked exactly one person, age, 2 years of age. We asked exactly another individual, we asked exactly only one individual who happened to be 3 years of age. You will usually have a lot of repetition in your inputs. But I haven't used that kind of repetition. And you can actually tell it, you give it the Y, the raw data, you do tilde, which on my keyboard is shift hashtag. And we also do yes, ask.
You mentioned 1 year of age, 2 years of age, 3 years of age.
Yes.
But 1, 2, 3 represents the people, no?
No, you're not counting people. Do you remember when we had I don't know
As
if
in
it's,
you observe the
yes,
observation.
yes, but the observation is made up of input variables and output variables. Let me show it to you this way. Let me show it to you this way. Didn't we have this earlier? Alt and R. This one. And probably isn't going to make a difference, but let me put it up here. You need to think of these two as the axes as some kind of variable. Now, variable could be hair color. It could be your favorite film from the Harry Potter franchise. In this case, just as a simple example, we said each point, so let's take this one. This observation is, we asked a 60-year-old, we asked one 60-year-old. So I'm assuming that the x-axis is age. Doesn't have to be age. I asked one 60-year-old, how many hours of a certain program or a certain type of television show does he or she watch on a weekly basis? And the 60-year-old told us, weekly, I watch 11.34 hours of this program. That's your data point. Then you will look at the input components and the output components. We are saying that 60 is the input, and we're going to try and predict the output.
Yes.
So what is your question exactly? Let's go back to R. What is your question exactly?
No, I think you answered it. I asked
Right, yes.
the
Yeah,
1,
you
2,
asked.
3, 4. I thought they were as
The
in
number.
person 1, person 2.
Yes, yes. Each let's look at head empirical. Each row represents your first data subject. We're taking people over here. It could be companies, it could be countries, it could be atoms, it could be fruit. Each row represents a specific data subject. But let's make it clear. You could be, I don't know, at an old people's home, for example, and a lot of the data subjects will all have the same age. So you could have maybe 40 rows of data where person number 50 is age 67, person number 51 is also age 67, person number 52 is also age 67. What might be different, and it might be the same as well, what might be different is how many hours they watch of a specific television show on a weekly basis.
All right, yes, it's clear now.
Very good. Very good. Keep them coming. Now what I'm saying, class, is that there's this function called LM in R. And if you do question mark LM, you get a description of what it does as one gets for any kind of function. And if we just read it, which is what we usually do in these sessions, LM is used to fit linear models, including multivariate ones. What does that mean? It means that you could have multiple input variables. We're only looking at age over here, but besides age, you could look at, for instance, the number of hours of free time, the number of hours of overtime that someone does. Who knows? Maybe the more overtime someone does, the less hours they do watching the specific program that we have in mind. And I'm going to say the y variable against the x variable, which is this. And if I do Control Enter, we have our least squares regression. And I could enter this into Desmos. And it's actually quite close to what I took originally. Let me show it to you. Y equals can I? Yes, I can. I can just copy and paste from the console. So I took this, whereas least squares regression gives you this linear relationship. It gives you the orange relationship. And that's all from RStudio. It's very straightforward. You just tell it lm, you give it the output variable, you're trying to predict the output variable, and it gives you the, excuse me, it doesn't, it's a bit early to be speaking of what it gives you. You need to give it the output variable and the input variable, or the input variables. In fact, the documentation very early on tells you including multivariate linear models. So if I remove the blue line, we now have something quite similar to what the book is doing. So the book is saying you have the simulated data based on this black curve, and one of the models is linear regression. This is what we've just done right now. There are two other models. We're not going to discuss them today.
Sorry, what does the orange curve represent?
So your data, and data is plural, but I'll use singular. Your data is.
In fact, one of
dots.
our lecturers mentioned this debate.
I would imagine, yes. Yeah, I
And
would
she
imagine.
says she thinks that data is plural. She uses the plural.
Yes, yeah, why not? I guess, are you treating it as a collective, or are you looking sort of as at the individual data points? So
I agree with you, to be fair.
well, I mean, grammatically, I think it should be plural, but I just guess it's a force of habit at this point.
Mhm.
Your data is the circles, is the points. Your data was generated. Now, this will never happen in practice. In practice, you will never have the black curve, but we're playing, I like to refer to this as we are an omnipotent being. We know the true relationship. You will never know the true relationship. So in many ways, we've worked backwards today, just like what the book is doing. So ignore the black curve. Pretend you're not omnipotent, neither am I. So ignore the black curve. The raw data is these circles, is these points. So to take a specific point as an example, 70.
And I think this is why there is the error element, because of the black curve, which is not accurate.
Well done, well done. The black curve only describes the relation. The black curve only describes the relationship between, let's take green, between this input variable and the output variable, let's use pink, that we're trying to predict. Now, this is usually one of the fundamental limitations of any model. And I'm referring to, you're not allowing for all the different factors that impact the output, that influence the output. Now, since we haven't allowed for all of them, there is going to be an error term. And the error term, that's our epsilon. And why not use color red, which is a bit appropriate. The error term is these red arrows.
And that is why you have a different error term for each.
No,
Or
no,
not.
no, no,
Imagine.
no. A lot of what you're saying is correct. A lot of what you're saying is correct. However, I think the best way to describe this is that each data point is influenced by the same error term. So, for example, each fair coin is influenced by the same 50-50 heads or tails. But
Mhm.
then when you run the experiment, each coin toss will give you either a heads or a tails. And that is what is called a random variable. And I'm not entirely sure in your case if it's going to be this year or the following, but you're going to have entire study units and exams which will involve each question testing you on one or multiple aspects of this concept called a random variable. The thing is that you're applying your A-level knowledge, and your A-level knowledge, everything is deterministic. So you were hoping, originally you asked, shouldn't each error term be the same
Mhm.
for each observation? Because it's just epsilon. It's not epsilon of X. It is the way it is written, it looks like a constant term, +5, +7. But in reality, it is a random variable. Now, what is a random variable? Just think of a coin. Just think of a coin. It might land heads, it might land tails, and there is a probability associated with each outcome. The error term is doing something similar. The error term might be practically zero. If you can see my cursor, the error term over here for this data point looks as close as it gets to zero, or else it could be quite pronounced. For instance, this one. And each red arrow, the length of each red arrow, has a probability associated with it. That's the information that the error term contains. So think of vectors. Vectors contain, to a certain extent, two pieces of information, direction and magnitude. The error term contains sort of like two pieces of information, the possible outcomes, so heads, tails, the length of the arrow, which is numerical, as well as the probability distribution of each possible outcome. So theoretically, the way epsilon works, you could even have an error term of 1,000,000. And just think of an arrow going all the way down or going all the way up. But that probability would be 0 point. I'm going to invent, but 1,000,000 zeros and then ending with a 1. That's what the error term contains. It gives you an idea of number one, the outcome. And we have positive and negative outcomes over here. It's a numerical outcome. It's no longer heads or tails. We interpret a positive outcome to give us, once you add the f of x, a data point above the black line, and we interpret a negative outcome in this context as a red arrow like this one, or like this one below the black curve. Now,
Do you have an
yes?
error term of 0
Yes.
where the gradient is 0?
No, I really wouldn't think, I really wouldn't think of it as gradient. It is where you would have an error term of 0 where the data point lies perfectly on the curve.
Ah, all right.
Right?
It happened because it's
That's a
coincidentally it
coincidence.
happened.
Yes.
That's
Yeah,
the gradient is
that's a
over there.
coincidence. But look at this data point. For all intents and purposes, its error term is 0 as well. Okay.
Mm-hmm.
So that's just a total coincidence. But
because the curve passes through
yeah,
it, basically.
well spotted, well spotted. Now, and I'm mindful of time, but we can do a few more minutes. Now you have your data points. Think of data that you've collected through a survey. And you're plotting age. Well, I think I should start with the vertical axis, right? You're plotting weekly viewing hours against age. Now you only have, initially, you would only have the raw data. You wouldn't have any of these curves. So that would resemble what we have in Excel. Initially, this is what you would have. That's just raw data. You've collected your surveys, you've entered them into a database electronically, and you've asked Excel or whichever software to plot the data. This is called, you could refer to this as a scatter plot. And I think that's actually the technical word. Now, what you want to do is you want to make predictions. You want to predict, for example, what if someone is 110 years old? How many hours would they watch of this program a week? And it really depends on your model, because you could assume that the model does this, maybe your model does this, maybe your model does this. Who knows? Who knows? And in fact, we could really say we don't actually know. Our data doesn't really consider anyone who's 110 years of age. So it's not really a very good model for predicting the viewing hours of someone who's 110 years old. But we want to create a model. What is a model? What is a model? A model is, I want to have an idea. Someone who is, for example, 20.5 years old. I want to get an idea. I want to predict how many hours they're going to watch. And these are three possible models over here. You have your linear model, where you've plotted a specific line, which in many ways the line is great for example, if someone, assuming that the line is correct, you could just extend it and say, okay, if someone's 110 years of age, then we're expecting them to watch so many hours a week. Then you have your blue line, which better reflects the apparent non-linearity within the data. And then you have the green curve that maybe goes a lot further than the blue curve.
The closest, right? I think it's the most accurate.
It is the closest, yes. Very often this is a sign of a bad model, because not necessarily, but very often you don't want to. This might be an example of overfitting. You have maybe trusted your data too much. Your data is always a limited sample. You haven't spoken to everyone. You haven't surveyed every single individual that may contribute information to us understanding the relationship between X and Y. Now, how are we going to rank these models? One way of doing so is by calculating the mean squared error, because we want to reduce the mean squared error. And this is what we've been doing today. What we could do now is we could shift perhaps gears. I need to remember exactly how. We could shift gears, and instead of use the line that I took originally, just totally arbitrary. I just said, okay, let me, luck or otherwise, it's actually quite close. It's actually quite close. But let me see if there's a way of using this LM. This LM has just created a model. It's told us the y-intercept is 6.6, and the gradient, the parameter, maybe remember those betas from a previous session. Can have a look at them very quickly. These betas, this is the intercept, and this is beta 1. And that's it. We're only using one covariate.
One variable, right? Age.
Yep, exactly. Exactly. Yep, exactly. We've taken it as age. Now, I think there's a way. What if I do predict and I type, and I just tell it, someone that's 110 years old. Now that hasn't worked because probably I need to specify the model. Let's see. Let's see, predict. And that tells me it needs an object. 110. That tells me it needs. Yeah, so that's a bit disappointing. I don't seem to have managed to make it work. But you know what I could do? What if I do? I seem to remember. Let's see. If I type coefficients. Yeah, that works. And what if I say the first coefficient? Look what you could do. Look what you could do. You could say the first beta value, the second beta value. All I'm doing is I'm sort of drilling into the data, not the data, into the model. I'm saying, what is the first beta? What is the second beta? I could actually save them as beta naught and beta 1. Beta naught and beta 1. Ta-da. And now I can create my f hat function. F hat, I think I need to tell R that it's a function. So fun, if you just type fun, what's really great about typing fun and you tab it, it's going to give you the entire template. Let me show you the difference. So if I type function and I press tab, I just get this. And it's useful, but compared to this, and I tab, look at everything that it's giving me. It's asking me, what do you want to call your function? Let's call it f hat. And then I tab, what do you want to call your variable or variables? Let's just call it x. And what does the function actually do? And what I want the function to do is this. I want it to do beta naught plus beta 1 times x. Now I run it, and notice it's going to store it over here. So let me just run it. It stored it. I now have something called f hat. I don't know what this does. Okay. So just like clicking this gives you kind of like an Excel type presentation. Clicking this for a function object gives you the instruction of that function. It takes a variable x and it creates, or it depends on this formula. Okay, so let's type f hat of a 110-year-old. Ta-da, 12.33. And you can see that it makes sense because if I extrapolate to 110, we do have 12.338. And it's the same over here, 12.338. So now notice something. Can I give it multiple inputs at the same time? Can I give it the vector 1 to 100? Because that would be exactly the ages that we considered without repetition. And if you do f hat 1 to 100, to my knowledge, it doesn't work. Interesting, it did work. Because normally you have to vectorize Now I might be using a version of R that this is the thing with coding. Although I don't think so. Somehow we got, I'm going to call it, we got lucky. So now we have every prediction for every age. Every prediction for every age. And we could call this, we could call this our expectation. Our expectation. Now we have a vector that contains the expectation for each data subject. We so happen to take the data subjects as age 1, age 2, age 3, age 4. Usually you'd have data subject with repeated characteristics or overlapping characteristics if maybe we're looking at more than a single variable. And now I can calculate the mean squared error again. Actual, let's create the actual vector, which is empirical raw data. That's that, right? 4.08, 4.36. You remember these? 4.08, 4.36, etc., etc. Now I can create the vector. I'm going to call it the squared error vector, which does expectation minus actual. We're subtracting two vectors over here. This is the great thing about R. If we weren't using R, if we were doing it, for example, in VBA, you would have to create a loop. You would have to tell it loop from 1 to 100. Instead, all that functionality is built in. So if I subtract a vector from a vector, it's just going to do it very easily.
Loop is when you repeat, right?
Yeah, well done, well done. But it could be repetition, for example, like in table mode in our calculator. That's a loop. But each repetition is for a different input value.
For each data subject, right?
Now, in this case, it will be for each data subject. Well done. That's kind of the step that we need to make from our A level to whatever this is. This is my squared error. What? Not quite. That's the vector. So I need to sum. The squared error for every data subject. And I now create the mean squared error by dividing the sum of the squared errors by the number of data subjects. And I could just say the length of actual or the length of expectation. And notice now it's 5.05. So it's better than what we had earlier. Earlier we had 5.14, which is actually, really, I guess just a very lucky choice from my end. Now we have 5.05. In fact, the book goes on to say and we can end over here, that something about linear fitting, that by definition, linear regression, which is what we created when we ran the LM function, this LM function, linear regression gives you the linear model that reduces the mean squared error by definition. So there's a strong relationship between the way we define mean squared error and the way we perform linear regression. Linear regression gives you the orange model. I don't know if you have any questions.
I have a lot of questions there, but this was very interesting.
Anything specific?
The ones that were very specific, I promise I've asked them all.
Okay, so one second, let me stop sharing so we can upload this